of activity. So again, I hope you have followed, because even if you do not go through the SARs, that is, we can be able, even by looking at the structure, I hope you can be able to. And of course, our starting point, our prototype is phenbenzamine, whereby it has a benzyl ring and it has a phenyl ring, benzyl phenyl ring, aliphatic ethyl group, and of course, the dimethyl group, obeying all the structural requirements, but of course having minimum activity, as we have said, for structural modification. So phenbenzamine is a prototype. It possesses 2 nitrogens, and only one is basic enough to be protonated at physiological pH. And we are asking which of, because I've already shown you this nitrogen, is the one which is basic enough. Why is the second nitrogen, or the first nitrogen, or the central atom, why is the central nitrogen not basic enough for protonation at physiological pH? Can you explain? Can you give me an answer? This nitrogen not basic enough to be protonated at physiological pH. Can you give me an answer quickly as we move on? Why is this nitrogen not basic enough to be protonated at physiological pH? I see today you are very few, 29. Ukikuja kuanguka wale hakuji class, do not blame Dr. Kamau. Fortunately, I keep the register. So I'm asking this nitrogen here. Why? We have discussed this nitrogen severally, or such a nitrogen. Why is this nitrogen not basic enough to be protonated at physiological pH? Can you give me an answer, please? Can you give me an answer? Yes, reader. Anybody, please, let's get a quick answer. Very good answers. We are saying very good answer. The lone pair of electrons. Remember, the nitrogen is basic because it has a lone pair of electrons, which it can donate to a proton. But now, when it is directly attached to a benzene ring, that lone pair of electrons can come in and participate in the delocalized electrons or in the aromaticity of the benzene ring through resonance, and therefore the nitrogen will be electron deficient and cannot therefore be able to react. So the only nitrogen which is protonable, remember we said that these drugs must have a protonable nitrogen. That nitrogen is protonable at physiological pH. That's a good answer for Evans, Joseph, and Frida, and also Kiprop. That's okay. Then so we move on. So we are saying that is the terminal nitrogen, and why we are showing this is because we say that these drugs must have a protonable nitrogen. The amino group must be basic enough to be protonated at physiological pH. Of course, it obeys all the general. I don't have to repeat those things because we have already mentioned. So the first SAR, isosteric replacement, and the isosteric replacement is for the formation of where you put a pyridyl. 2 pyridyl produce the more potent tryprenamine. However, the 3 or 4 pyridyl, in other words, if you change this nitrogen, that's 1 pyridyl, 2, 3, or 4, cannot be considered isosteres and produce less potent compounds. So it is only when the nitrogen is at that position number 1 that gave us activity. You can see the structure is basically the same. All you have done is put a pyridyl group. SAR2 substitution, these are things we have mentioned. Para substitution with lipophilic groups, not only lipophilic groups, sometimes even, because even methoxy group, methoxy is both lipophilic and also hydrophilic because of the oxygen. So para substitution, lipophilic such as chloro, bromine, methyl group can increase Other substitution is highly undesirable, but it appears with the ring conformation. Meta substitution is either ineffective or unfavorable, but this effect must be due to electronic as well as increased lipophilicity. Thus, introduction of a paramethoxy on tryprenamine produces pyriramine, a more potent but less toxic drug. So we are only saying again what we had said. We had said about the positions. You can only do substitution, ortho, and meta. They are responsible active drugs. So pyriramine, so each and every drug, we're able to explain each and every drug, and pyriramine is as a result of para substitution of the benzyl group. And of course, we already have the pyridyl group. We can't change that. We have the pyridyl group, which is responsible for even better good activity. Before we get to antazoline, we have also discussed the others. We have discussed zonzelamine. We have said also substitution or replacement of the pyridyl group also with the pyrimidine group also resulted in increased activity. And then also we talked of so please do note that although I might not have explained them all again, it's because I've already explained them when we were looking at the various compounds. So from this, you should also be able to explain the others. Tonzelamine, methapyridine, we have already explained. So the final one, I think antazoline is an imidazoline derivative, but has 2 carbon chain that's generally included in this class. So we are saying it's an imidazoline, it's an imidazole derivative, but we include it in this class because the nitrogen, the central nitrogen and the terminal nitrogen are separated by 2 carbon atoms. That's why we basically include it here. But we are saying it is less potent than most antihistamines, but it's characterized by lack of, has lack of irritation, plus it has a local anesthetic properties, which makes it ideal for ophthalmic use. So it's mainly used drops for each and so on. As a class of the ethylene, means it has low to moderate potency with low anticholinergic side effects, low antiemetic effects, and moderate to high sedation. So the most important is the one that we have said, it has much lower, it will have lower activity, it is less potent. This is what is most important. It has less activity than the other antihistamines, explained by the fact that it is a secondary amine rather than a tertiary amine. Antazoline has lower potency, but as we had discussed earlier, as an ethylene because it is an ethylene, on top of it, that it will have also lower activity. It should have moderate potency with low anticholinergic side effects, low antiemetic effects, and moderate high sedation, because it used to cross the BBB. The synthesis that I will send to you for you to have a look. The syntheses are direct, so those. Any questions before I move to the ethanolamines? These are direct. If we have understood what we have discussed in terms of the general SARs, we can be able to move quickly. Then the ethanolamines, or what we are calling the amino alkyl ethers, again, they are bioisosteres of the ethylene diamines, whereby the nitrogen has been replaced with the carbon oxygen with retention of activity. So they're isosteric, where the nitrogen in the ethylene diamines has been replaced with the carbon oxygen with retention of activities. You can see they have slightly higher activity. The other ones had low. These ones have moderate H1 antagonist potency, high anticholinergic side effects. The other ones had low. So once you increase their activity in terms of antagonistic activity, you also give them the structure that will also bind the cholinergic receptors, and also the compound is able to penetrate the BBB much more and give us high sedation. So if you compare these to the other ones, we had said the ethylene diamines, we had said they had moderate potency with low anticholinergic activity and low antiemetic. So even these ones, we are saying they have high. They have also moderate antagonistic activity, but they have high anticholinergic activity and also high sedation. So their side effects, the side effects of the ethanolamines are much higher. And if we go back, we can be able to understand why these drugs will have also more anticholinergic activity. If you look at the structure of acetylcholine also has an oxygen, if I'm not wrong. The structure of acetylcholine has an oxygen, and because of, again, much more, so the ethanolamines have much more closer structural resemblance with acetylcholine than the ethylene diamines, and therefore they will have more binding. They will have higher binding affinity for the cholinergic receptors, but again, they do not trigger any activity. They sit there, they still behave as antagonists, and therefore responsible for the high anticholinergic side effects and high sedation. So we'll be they are being, of course, they are passing through the BBI and bringing us the sedation. So you're looking at the ethanolamines and propanoamines, and we just mentioned that the difference between ethanolamines and propanoamines is that in the ethanolamines, the central atom is separated from the terminal nitrogen with 2 carbon atoms, and in the that is where we have the pyridine ring. They are separated with 3 carbon atoms, and we are going to see that. So we have again here, the prototype is the diphenhydramine. So if you look at this, the major difference between the ethanolamines in terms of the aromatic groups is that these ones do not have the benzyl group. That again is what differentiates these drugs from the others, from the ethylene diamines. These usually have benzene rings or a pyridyl ring. Benzyl. Remember, for the ethylene diamines, all of them had the benzyl ring. So the diphenhydramine is where both rings are benzene rings and therefore this carbon will not have chirality, as we mentioned earlier. So again, you can see everything else is obeyed. It's a tertiary amine. You have those 2 groups, and of course you have the oxygen and you have the 2 carbon atoms. Then you come to the bromo diphenhydramine. The only difference is that there is substitution. There is a substitution, para-substitution on one of the rings, which we have already said that will increase activity. So that gives you bromodiphenhydramine, para-substitution of one of the phenyl rings. Then you remember I mentioned ofenadrine. Ofenadrine is a drug that has much lower antihistaminic activity because of ortho substitution. Again, structural resemblance with diphenhydramine with an orthomethyl substitution. That orthomethyl substitution prevents this molecule from obtaining the optimum non-coplanarity which is required to bind the receptor. Then you have the dimenhydrinate. Dimenhydrinate is just a sort of diphenhydramine, and theophylline and 8-chlorotheophylline. It's just a sort of the two to give us just to give us perhaps better solubility and so on, because it is a more polar molecule. Then you have carbinoxamine. Carbinoxamine, it is having two of the SARs. One, the phenyl group has been para-substituted with a chloro group. Para-substituted with a chloro group, and one of the phenyl rings has been replaced with a pyridyl ring. The effect is the same as for ethylene diamines, so that drug, we'll expect it to have much, much more activity than even the bromodiphenhydramine, because of the fact that you have replaced one of the, there's an isosteric replacement of the phenyl ring with a pyridyl ring. Now, if you look at this carbon here, that carbon is now a chiral. It's a chiral carbon. It has chirality. You know, when you say achiral, means there is no chirality. So this is a carbon which has symmetry, or it's a chiral carbon. That group and that group are different, and that group is different. Of course, it has a hydrogen. So again, there we'll expect stereochemistry to play a part in activity. So in a nutshell, diphenhydramine is the first or the prototype, and dimenhydrinate is a sort of 8-chlorotheophylline with diphenhydramine, and it is used for motion sickness. So that is just a sort. It still has diphenhydramine. As in the previous class, para-substitution with a bromo group in bromodiphenhydramine yields twice as potent as the parent compound, and we had mentioned that. So there is nothing new. Orthomethyl produces ofenadrine, an anticholinergic used as a skeletal muscle relaxant in muscle strains and sprains, and has very low antihistamine potency because of the orientation of the rings. And I have said orientation of the rings is not good, because the orthomethyl group distracts, brings obstruction, and therefore these two rings, because of the steric hydrons introduced by the methyl group, are not able to obtain the optimal, as I said, non-coplanarity, which is needed for the activity of these drugs. Next, isosteric replacement of the phenyl by a 2-pyridyl results in a slight increase in potency, but when combined with a parachloro substituent to produce carbinoxamine, it becomes highly effective, increases the potency. So there's a 2-pyridyl, increases the activity, as we had said earlier. Now, when you do a chloro substitution to give us carbinoxamine, then you increase the activity further. The chloro group increases the lipid water partition coefficient and, of course, metabolic stability. Remember, anytime you put a halogen in a phenyl ring, halogens decrease metabolism of that ring, because they metabolism because of their negative steric effect. You know, halogens have both resonance and also negative inductive effect, where they pull away the electrons. Although they will contribute electrons to the system, their effect, their negative inductive effect is predominant. It is much stronger. Yes, they will contribute electrons through resonance, but their negative inductive effect, their power to pull electrons due to their high electron dominate, and that is why they deactivate the benzene ring by pulling electrons through a negative inductive effect, and therefore decrease the metabolism of that ring through oxidative hydroxylation. So that makes that molecule to even have a longer duration of activity, and of course also to have higher lipid solubility, and therefore penetrate the membranes more, and definitely also penetrate the membranes and also give us. So as we have said, that is carbinoxamine. That is this is the so they are, we haven't mentioned all of them. Again, when we look at them here, we are able to understand the differences. So that's carbinoxamine, pyridyl group, and cross substitution, diphenylpyrarine. If you look at diphenylpyrarine now, diphenylpyrarine has a piperidine ring. The diphenylpyrarine has a piperidine ring, and if you count now the number of carbon atoms separating this oxygen and the terminal nitrogen, you find it's 1, 2, 3, 1, 2, 3. Although they are apart, as we said, they can be part of a piperazine ring. And that's why I told you we'll go back after this and you give examples. So if you talk about diphenpyrarine, it is an example of a propanoamine. 1, 2, 3. The oxygen central atom is separated from the whichever way you go, 1, 2, 3. Because if one side was 2, we'd go with the shorter side. But whichever way you go, separated with 3 carbon atoms, 1, 2, 3. So diphenpyramine, diphenyl pyramine is an example of a propanoamine. It is not an ethanolamine. This is an ethanolamine. The oxygen and the nitrogen are separated with 2 carbon atoms. This is an ethanolamine, 1, 2. If you look at clemastine also, the pyridine ring, diphenylpyrrolene has a piperidine ring. Clemastine has a pyridine ring. Now, if you look again at the number of carbon atoms from the oxygen, 1, 2, 3, you got the shorter side. 1, 2, 3. So again, for clemastine, the oxygen, the central atom oxygen is separated from the terminal nitrogen with 3 carbon atoms. So again, also, so clemastine is a propanoamine, not an ethanolamine. It is an alkyl amino ether, but it is a propanoamine because of 1, 2, 3 carbon atoms. Again, clemastine is an example where the terminal nitrogen, unlike in diphenhydramine, here it is only 1 carbon, which is part of the pyridine ring with retention of activity. For diphenylpyrrolene, actually all the 3 carbons are part of the piperidine ring with retention of activity. The other thing we note in clemastine, is that because of this carbon attachment here, this ring, when you have a single bond attached to a cyclic ring, you can have geometric isomerism. When you have single bonds attached to cyclic rings, that bond is rigid, and you can have geometric isomerism. So for clemastine, you can have both the R and the S, and you can have the C's. Yeah, you can have geometric isomerism, and not even geometric isomerism. The most important is that this carbon here, I will go to the geometric isomerism. But if you look at this carbon here is a chiral center. So there is this carbon here. Here, this carbon is a chiral center. That's one a different substituent. That is a different substituent. So this is a chiral center. If you look at this one here also, this is a chiral center. So what we are noting is that clemastine has 2 chiral centers. It has a chiral center there, and it has a chiral center there. It was noted that the chirality further from the nitrogen has the more predominant effect than the chirality of the carbon much closer to the terminal nitrogen. Again, we are going to look at that in a short while. But please note, for clemastine, it's a propanoamine. It's a propanoamine, and also for clemastine, unlike like doxylamine, you can see it has a 1 chiral center there, because this is different, that is different, that is different. Carbaminoxamine also has 1 chiral center, but clemastine is unique in that, unlike the others, it has 2 chiral centers. So ethanolamines and propanoamines, SAR3, several of these compounds have chiral centers. So we have not bothered to go back because you have all those other things we have discussed. Now we are introducing what's most important, chirality. They have these compounds have chiral centers, that's the ethanolamines and the propanoamines, where one isomer is more potent. Thus, levo S, carbinoxamine, was found to be more potent than the dextro R. So the levo S more potent than the dextro R. This implies that the receptor must possess a degree of asymmetry or stereochemistry in the area where the rings bind in order to account for this. When we come to look at the binding, we will find that because these aromatic rings are very huge, surely they cannot go and fit where histamine was fitting. So they must be binding outside. You see, where histamine binds, they must be binding slightly outside or the area surrounding the histamine receptor. And that area must be the one which is also exhibiting chirality and allowing for one of the isomers to have much higher activity than the other. So we are only saying that the receptor possess a degree of asymmetry in the area where the rings bind. You can see it is very clear in the area where the rings bind. And as we are going to see, the rings cannot fit in the area where histamine binds. They must be binding in the adjacent areas to the actual receptor because they are very big. And that is the area we are saying it must be allowing for stereochemistry. Replacement of the central hydrogen by a methyl general results in a slight increase in potency. Again, if you look at doxylamine, that's all we are saying. This, if you put this CH3 here, this drug, of course, it's slightly different. It's not very similar to any of the others because this also has a chloro group. But we are saying it was found that when this hydrogen when the hydrogen which was here was replaced with a methyl group, like in doxylamine, again, that also resulted in increase in activity. Remember, we are only highlighting the SARs, but all the other SARs that we have mentioned before are also applicable. This implies that the receptor, that one you have already done, SAR4, phenylpyrrolene, and clemastine have 3 carbons separating the oxygen and the nitrogen atoms. Thus, they are proper noamines that we have already mentioned. Lengthening the chain increases potency and also gives these compounds a longer duration of action. So both diphenylpyrrolene and clemastine, they are proper noamines. Remember, we did mention much earlier in the general SARs that the separator, the spacer, can either have 2 carbons or 3 carbons. So an example of where it has 3 carbons is in the proper noamines. And when there are 3 carbons in the proper noamines, there is increase in activity, in potency, and also in the duration of activity. Clemastine is a long-acting agent with duration of action of up to 12 hours. So that means clemastine is a drug we can give BD twice daily rather than 3 times daily. The dextro, the tertiary isomer, is RR at its 2 chiral centers. Comparison of all phosphodiastereomers indicates that the configuration of the center close to the nitrogen is not as important as the configuration of the center close to the rings. All we are saying is this. What we are saying, as I had already explained. If you look at clemastine, it has this as a chiral center, it has that as a chiral center. It was established, and that's why we are saying, although we cannot say that all of them, the S or S isomer is more active. You can see for carbinoxamine was the S isomer, for clemastine is actually the R isomer. So the most active isomer was when this carries an R configuration and this one carries an R configuration. When this is an R and that is an R, that isomer has the maximum potency. Now, I want you to think it out and try to get the order. That's clemastine. Try and give me the order of activity as when you compare the different enantiomers. When you compare the different stereoisomers, what do you expect the order of activity to be? The most potent is when this is R, this is R, and this is R. Which would be the second most active isomer? And which is the that is what I mean by order of activity in terms of the stereochemistry of that molecule. What would you expect to be the order of activity in the various diastereomers? Class, can you give me the order of activity? The most active is RR, which will be the next active. Is the question clear? Order of activity governed by the stereo of the first chiral and second chiral centers. Remember, we have said this one does not matter as much as this. The one which matters most is the one next to the aromatic groups. But nevertheless, it also has some importance. I have the first one. From Evans Marwa. Anybody else? Any other suggestion? Or the same suggestion? Can I get answers, surely, students? Only the same students answer questions. Can I get answers? Can I get answers? Anyway, I will not take too long because I also want to move on. So Evans, thank you very much. That's a correct answer. That you expect the order of activity is when the first most active is when this is R and that is R. The next one you'd expect is when this is R and that is. One you'd expect is when this is S and that is R. The last one is when they are both SS. I hope you understand. At least Evans got it correct. We are only saying, and what we are saying here is that the order of the stereochemistry of these groups is very important in terms of activity. The dextro, because we are saying the most active is when both of those both of those centers. And then we have stressed that the configuration of the center close to the next not as important as the configuration of the center close to the rings. So when that center close to the ring carries an R, you expect maximum activity. But of course, when both carry R, you expect highest activity. So RR, that's the order is RR greater than RS, greater than SR, greater than SS. Although a modern agent, it has sedating side effects also. So it also has sedating, clemastine also has sedating effects.